Hi guys, we're on slide 24 of the chapter 5 PowerPoint. We are going to solve for the third and fourth ways to find delta H. We've done calorimetry, we've done Hess's law. The next two methods are actually pretty similar to each other. Number 3 is going to be finding delta H reaction using the heat of formation values that can be found in the appendix of your textbook. Okay, so if you look in the appendix, appendix B we referred to before has a lot of the constant values that are useful for water, the specific heat, the heat of vaporization, the heat of fusion, all that kind of stuff. If you go to the next appendix, it has a lot of thermodynamic values for many compounds, okay? It has the delta H of formation, which is what we're going to use right now. It also has the entropy value for that compound and the Gibbs free energy value for that compound. Those are things that we're going to use in 1212, but for now we're just going to use delta H, okay? So we're going to look those numbers up in just a minute, but the method we're going to follow, the heat of formation is the amount of heat that it takes to make 1 mole of a compound from the elements that it's formed from, okay? So like if I want to make 1 mole of water from hydrogen and oxygen, it's the amount of heat. It's like the hydrogen and oxygen have a certain amount of internal energy stored in their molecules. When I make the water molecule, it has a different amount of energy in that molecule. The difference between them is the heat of formation, okay? So that's the number that's listed in the appendix. The appendix is always going to be specific to making 1 mole of a compound. And what we're going to do is to find the delta H for a reaction, we're going to look up the delta H values for all the products first, because the appendix gives us the numbers to make a compound, and the products are the compound in a reaction. We are making the products. So the numbers in the appendix are going to be set up perfectly for our product values. And what we're going to do is we're going to look at all the products and we're going to do a summation. We're going to add together all the product values first. Then we're going to subtract all the heat of formation values of the reactants. Now, why do we subtract them? Well, when we do a chemical reaction, we are forming the products. So the numbers in the appendix, the way they're written, are perfect for the product part. But we are not forming the reactants. We have, in a reaction, we have the reactants in the beginning, and we're going to destroy them. We're going to tear them apart and build something new. So the heat of formation value is actually the opposite of what we want. We're going to change the sign, or if I subtract the number from the appendix, that's going to change the sign for me, okay? Now, you really don't have to overthink it all. Essentially, if you look in the appendix and get the numbers for all the products, and then subtract the numbers for all the reactants, then you're going to get the right answer. Okay, so now I'm going to show you, if I go out of the PowerPoint for a minute, if you look in the appendix, it's going to look kind of like this. Now this is not a very good picture, it's from one I just pulled off the internet, but essentially each, the way it's organized is a group of compounds that relate to one element are all put together. So this is like a middle page of the appendix, but it's got a bunch of compounds that have iron in them, and a bunch of compounds that have lead in them, and a bunch of compounds that have nitrogen in them, and a bunch of compounds that have mercury in them, okay? So there's different elements that are grouped, like all the compounds related to that element are together, okay? And then it gives you the name of the compound, and then the first column of data is delta H, the second column is delta G, and the third column is S, which is entropy, okay? We're not really worried about the second and third columns right now. We only want to look at the first column, which is the delta H values. So at the top it says delta H. You find the compound you want, you write it down, okay? So that picture is not very good for us right now, but I pulled up another table where they had already pulled what we want. If you remember, the reaction we're trying to find was, we're doing the same one as before, where it's 2 sodium plus 2 waters yields 2 sodium hydroxide aqueous plus hydrogen gas, okay? So that was our reaction. we're going to look up the values. If we look in the appendix, the sodium hydroxide, and you have to be specific to the physical state. So this is a table somebody else built that I'm just kind of using. Sodium hydroxide aqueous, in order to make 1 mole of that compound from the elements, it's going to release it's negative 470.1 kilojoules per mole, which means to make that compound is an exothermic process from the pure elements. Okay, so that value, we need to write that one down. Then we're also, water is our reaction, so we need to write down the value for water, which liquid water is negative 285.8 kilojoules per mole. Okay, those are the two numbers that we need. Now, if you look at our reaction, which I'll go back to it now, in our reaction, we also, we have to look up delta H values for everything, okay? Well, the sodium, if I asked you how much energy does it take to make sodium from the pure element, well, this is the pure element. How much does it take to make sodium from sodium? The answer is 0. We're using the element itself here. The heat of formation of a pure element is always going to be 0. So if you look in the table, in the appendix, you can find it, and it says the delta H of formation for solid sodium is 0. If you look up the heat of formation for hydrogen gas, H2 gas, its heat of formation is also 0, because that's the normal form of the element. Okay? And in order to form the normal form of an element from the normal form of element is always 0. So essentially, I got all my numbers. We've looked them all up now. My products are going to go in front. So we looked up sodium hydroxide. I think it was negative 470.1 kilojoules. That's per mole, but I'm going to have to multiply that by 2 because I need to make 2 moles of that. So I'm going to have 2 times negative 470.1 plus 0 for hydrogen. So my products is just going to be 2 times negative 470.1 minus my reactants. Well, the sodium value is going to be 0 because elements always are. And then the water value that we looked up was negative 285.8. But again, that's for 1 mole. I need to make 2 moles. So it's going to be right here, 2 times negative 285.8. So I'm going to have 2 times negative 470.1 minus 2 times negative 285.8. And if you do that math, it should come out to be basically the same value that we had the previous way that we found this delta H value. Okay? So that is how the heat of formation values are used. Honestly, that is probably the easiest way to find delta H most of the time, because when you're working a problem, you should always have your textbook with you. And anytime you have a reaction, if you just look up the heat of formation values and do the sum of all the products minus the sum of all the reactants, that gives you delta H. That is there's no trick to it. It's very simple. You just have to practice it enough times that you can do it quickly. Okay, so that's the method for heat of formations. Okay, that slide just has a repeat of what some of the values is. Specifically though, standard enthalpy of formation, the delta H of formation for a pure element is always going to be 0 if it's in its normal form. All right, so now that brings us to our 4th method to find delta H. This one is kind of similar to the heat of formations, except instead of looking at the molecules, we're going to look at the bonds. Okay. Now, this method is actually talked about in the book in chapter 8. Okay, but since it matches up, like we're talking about ways to find delta H, this method fits with this material. The only problem though is that in order to follow this method, you have to know what the structure of the molecule looks like. Like when you draw like carbon dioxide, you have to know that the carbon atom has a double bond to one oxygen and a double bond to the other oxygen. You have to know what the structure looks like, or you can't figure out how to set it up. Okay? So in this section, it's really important. I'm going to give you the structure. So I'm going to give you a picture of what the molecule looks like, and from that, you just have to be able to pull the information that you need. Okay? Now, when you work a problem like this, you will have to look at chapter 8 to find the information you need. So again, I have a tab pulled up. So you're going to look up in chapter 8, or just look in the appendix at the back of the book. The table is called bond dissociation energies, or bond dissociation enthalpies. Okay? And essentially the table is usually broken into like single bonds, double bonds, and triple bonds is how they usually organize it. But I need to find out when I break a bond, like a bond between two hydrogen atoms, the strength of the bond, the amount of energy it takes to break that bond, is going to be 436 kilojoules per mole. Okay, so that's the number I would need. I would write that down. If I want to break an HCl bond, that's going to take 432 kilojoules per mole. Okay, and then if I want to break, it doesn't have it on this table, but we'll find the ones that we need for our next one. If I want to break a CC bond, it's going to be around, again, it can vary a little bit based on what's connected to it, but around 370 something kilojoules per mole for a single bond. If it's a double bond between two carbons, it's going to be 730 kilojoules. If it's a triple bond between two carbons, it's going to be like 964 kilojoules, okay? So if you see the structure in front of you, and again, I'm going to provide the structure to you, you just have to decide which bonds are present in the molecule, and then based on that, you look up the energies from the table that you need, and then we do the math, okay? So let's go to our equation. So when we're doing these, our process is going to be very similar to what we did a minute ago with heat of formations. Heat of formations, we look in the appendix, and I said that you're going to do the products minus the reactants. Okay? With bond dissociation energies, it's going to be the opposite. It's going to be the summation of the bonds broken, which are the reactants, minus the summation of the bonds formed, which is the products. So method 4, if I'm using bond dissociation energies, it's going to be the opposite of method 3. Method 3 was products minus reactants. Method 4 is going to be reactants minus products. Okay? So, and then a limitation of this one, it only works with covalent molecules because we have to have covalent bonds. That's what the energies are that we're talking about. And it has to be gaseous molecules. So this method can't be used all the time. It can only be used on certain cases. So, if I have this reaction, now again, the balance equation is on top. I have a CH4 molecule reacts with two O2 molecules to form a CO2 and two water molecules. Everything is in the gaseous form. And if I want to find delta H of this reaction, I can find it by looking at their structures. So again, I told you I was going to give you the structures. So the CH4 molecule, there's a CH bond between carbon and each of the hydrogens. So there are a total of 4 CH bonds in this molecule. 1, 2, 3, 4. It reacts with an O2 molecule. Well, if you draw the structure of O2, it has a double bond. But the balance equation said there's 2 of them. So I actually have to have 2 O2 molecules right here. Then a CO2 molecule, which looks like this, and then 2 water molecules, which look like these. Okay? Now, when I set this up, again, I told you we have to do the bonds broken in the reactants minus the bonds formed in the products. So if you look up the numbers, the CH bond right here, the number we need is 413. That's the bond energy, that's the amount of energy it takes to break a CH bond. But I need to break all 4 of them. So it's going to be 4 times 413. Then I need to break the double bond between the oxygens. So each of those, if I look in the table, is going to be 495. But I got to break 2 double bonds, so it's going to be 2 times 495. So I'm going to add all that up. That goes in the front of my equation. Those are the bonds I'm breaking in the reactants. Minus the bonds formed. Well, when I look here, a C double bond O, the energy of that is 799, but I got to break this one and that one, so it's going to be 2 times 799. I'm forming those bonds, which is why I'm subtracting it, because it's the opposite of what the table was. So I've got the CO bonds, now I've got the OH bonds, 1, 2, 3, 4. Each one, the table tells me 463, but since there are 4 of them, I multiply by 4. So the setup's really easy if you just look at your structures, count how many of each type of bond there are, and just do the bonds and the reactants minus the bonds and the products. That's the whole process. And if we do that, this is a different reaction from the ones we've done before. So again, the answer here is going to be negative 808. So you can do the math and check it yourself. That's how we find delta H by bond dissociation energies. Okay, so we've now done all 4 methods. That is pretty much the end of the chapter that we're going to talk about. I just want to cover a couple of quick things. Number one is, why do we have these 4 methods? Like, why do we need them? Well, essentially each one kind of serves a different purpose. Okay, all delta H values, when they're originally determined, is through some sort of an experiment where you go in a lab, you measure the heat changes that occur. So calorimetry is the basis of all this. Okay, we get all the original numbers from calorimetry, but then once somebody has determined the values for forming certain compounds and certain reactions, then we want to build all these tables that we can use as references. So whether I'm doing Hess's law, where I'm using reference reactions, or if I'm doing heat of formations, where I'm looking at reference values for the heat of formation of certain compounds, or I'm using bond energies, where I'm determining how much energy is involved in a bond. For all of those, they're just different approaches to solving these for these values, that some may be good in different cases. Okay, so that's the end of the 4 methods. The last thing I want to talk about, actually, I'm not going to finish the rest of the PowerPoint because it's very it's more examples of the same things, and I may make another video where I'll kind of work through examples again later. But for now, the last new topic that we need to talk about is nutrition. In thermochemistry, one of the kind of everyday examples that we come across is energy in food. Okay, and it doesn't really fit in anywhere else during our semester, but it is something that's relevant to what a lot of you guys are going to do, whether you're going into a health field or nutrition or physical therapy or whatever. Okay, so how do they calculate, like if you eat a candy bar, how do they calculate the amount of energy that your body can derive by burning that fuel? Okay, well, essentially when you eat food, there are 3 main components of the food that your body can get energy from. There are the carbohydrates, which are the sugars and starches. There's protein, and then there's fat. Okay, fat or lipids or whatever. Okay, each one of those kind of has a characteristic amount of energy that your body can get from it. When you eat 1 gram of a carbohydrate, your body will get 4 kilocalories of energy. Okay, now it's actually kind of important. We talk about calories. Generally, when we talk about calories in nutrition, we say that a normal person will consume about 2,000 calories per day. But those are not normal calories. A nutritional calorie should always be written with a capital C, and it actually stands for kilocalories. So 2,000 calories with a capital C, that's a nutritional calorie, is actually 2,000 kilocalories in normal units. Okay? Now, it's not usually written that way because for a lot of people, if you told them that they were eating 2,000 kilocalories per day, and then if you convert that into regular calories, it's actually 2 million calories with a little c. Those numbers just kind of bother people. They don't like to deal with those, okay? So in order to make it smaller, The nutritional calorie is just a capital C instead of the kilo in the front. All right, now, a nutritional calorie, if we eat 1 gram of carbohydrates, 1 gram of carbs, we get a specific amount of energy from that. It's called the fuel value. And the fuel value for carbohydrates is 4 nutritional calories. So 1 gram of carbohydrates is going to give you 4 calories of energy that your body can use to do work. Okay? Now, if I eat 1 gram of protein, I will actually get about the same amount of energy, 4 nutritional calories. Now, it's really not exactly the same. These are rounded to 1 sig fig. I think one of them's like 3.8, and the other one's 3.9 or something like that. But we simplify in here. We're just going to call it 4 calories each for carbohydrates and proteins. But then if your body needs to store energy in a more efficient form, the best energy source for your body in terms of the amount of energy is going to be fat. 1 gram of fat, if your body were to burn it, will give you 9 calories of energy. Okay? So, if you eat too many calories in your daily diet and your body can't burn all the carbs and protein, then your body converts some of that into fat, and that's a more efficient way for your body to store it. So, those are our values that we need. Now, let's just say if you eat a candy bar and you want to know how many calories you're going to get from it. Essentially, you have to use these ratios. It's 4 calories per gram for carbohydrates, 4 calories per gram for fat, for protein, and 9 calories per gram for fat. So if you look at the nutritional label for a candy bar, or a can of Coke, or any other food that you get, they calculate it based on these values. So if I drink a can of Coke, I think a can of Coke has about 40 grams of sugar in it. So the number of calories in a can of Coke would be 40 grams times 4 calories per gram. I can make that into a conversion unit. So it's going to end up being 40 times 4. It's about 160 calories. Okay, so if you look at a can of Coke, look on the back at the nutritional label, it'll say somewhere around 160 calories because there's about 40 grams of sugar inside of it. Okay, now if you actually measure out 40 grams of sugar, like pour it into a beaker on a scale, you'd be amazed at how much sugar they actually dissolve into a can of Coke. It'll blow your mind. Now, let's just say if I eat a meal at McDonald's, okay, eat some fries. Fries are going to have a lot of starch in them, which is carbohydrates, not much protein, but then when you fry in grease, you're also going to have some fat. So if I get a certain number of calories from carbohydrates, some from protein, and some from fat, once I figure out how many calories I have from each, then I'm just going to add them all together to get the total. Okay, so you guys need to be able to handle simple problems related to these numbers. I think you should memorize these numbers, especially if you're going into any kind of medical or exercise-related fields. These numbers are very handy to know. Okay, so that's it. We are pretty much done with chapter 5. If I get a chance to, I'll do one more video later with just some practice problems and stuff. But hopefully you can be working on that yourselves too.